we talked about reaction feasibility using Gibbs free energy. Uh, so today we are moving on to another new topic under advanced physical chemistry. It is on rate equations. So this section is not that hard. Rate equations. So under rate means how fast the reaction is happening. So under that we will be learning about rate equations, deriving rate equations, rate equation calculations, rate is equals equilibrium. No, no, no. No, they are totally different, right? When the rate is zero, it is equilibrium. Rate means how fast reactants are becoming products. So when the reactants are not getting converted into products, reaction is in equilibrium. So forward reaction and backward reaction are happening at the same rate, right? It's entirely the opposite rate or zero rate, right? Then it is equilibrium, right? Rate. And the Arrhenius equation. Arrhenius equation. Then the finding activation energy. Finding activation energy. Concentration time graph. Time graph. Rate concentration graph. Rate determining step. Okay. Right. So let us move on to rate equations. Right. Rate equations. Now rate is about how fast the reactions are happening. Right. So is this the first time you are learning about rate in A levels? So you haven't studied anything for AS? Right, remember now. Yeah, there's a path usually in the ASS also. So you must keep those few things in mind. So we are going a next step, right? Um, Now rate equation means rate is equal to delta or difference in what? Products over time, delta t, right? So, but the thing is, we can write the rate equation. You can find the rate using this equation, using the amount of products being produced. But the thing is, if you are using finding the rate of a reaction with the reactants, it must be negative d reactants. Can you tell me why? Why it must be negative? Why? Very good. Very good. Over time, reactant concentration is decreasing. So final minus initial, you will get a negative value. So therefore, we are making sure otherwise, you will get a rate as a negative value. To avoid that, you are using a negative sign. Right? So both with the products and the reactants, you can find how fast the reaction is happening. Can you tell me what are the units? What should be the unit there? Change of concentration over time. Change in concentration is what? Usually it is measured in moles per decimeter per second. Per second. Right. Uh, Now what I would do is I will give you some data. I want you to plot a graph, rough plot. Right. Right. This is the first of all, when you are plotting the graph or when you are doing anything, there must be a stoichiometric equation. Stoichiometric equation means there is a reactant called D. In aqueous medium, it is becoming a product, right? So, right. So this is the delta D. Change in D, change in D when the D concentration. When the initial concentration of D is 3.0, the rate is observed as 3.00 into 10 to the power of minus 3. When the rate, when the initial concentration is taken as in a second reaction, let's say you are starting off with this at that moment. Initial rate means at the beginning. That is called initial rate. At the beginning rate was this. And when the initial concentration was taken as this, the rate came as 6.60 into 10 to the power of minus 4. Right? I want you to plot a graph rate versus concentration. Plot a graph. There are 3 points, right? Pick a scale and sketch. It won't take much time, right? Okay, so it is what? Roughly, it is what? It is what straight line. So you can tell in this as per this reaction, from reaction to reaction, it may change. So we are doing an experiment. We found out the rate is, it depends on one reaction to another reaction, right? From the reactants, from the products, from the conditions. Rate is proportional to what? Concentration of B here, right? What can you tell about gradient? Negative or positive? Here, rate equals K D, right? This K means what actually? The gradient of the graph. Gradient. So here, so that is why we can tell it is proportional. Rate is proportional to the concentration. Why? The gradient is constant, right? So here in this equation, K value is represented by the gradient of this graph, right? So there are many different shapes, depends on different reactions. For this example, we have taken the easiest type of relationship to learn, right? This is not the only relationship, right? But this is the simplest type of relationship we can learn, right? Now, even though we were discussing about rate equation, that is not the actual rate equation, right? That is the way of finding the rate. Usually, rate equation, the thing called rate equation, has these features, right? Now we are coming on to our rate equation in A2, right? Rate equation. To write a rate equation, first of all, you should know the stoichiometric equation. Right? Let's say uh, A and B reacting together to form the product C, right? And A and B, right? A and B are reacting together to form product C, right? So we haven't balanced it. We don't know the stoichiometric ratios, right? And then for this reaction, we can write a rate equation. Rate equals K A to the power of A into B to the power of I'll come up that B to the power of B, right? A to the power of A and B to the power of B. This A means, right? This A means order of the reaction, right? Order of the reaction with respect to the concentration of the reactants, right? Okay. Yeah, wait. That is what we are going to learn. The whole, yeah. Second one is the order of the reaction with respect to B concentration. Right? That is the whole lesson is about, right? That is what we are coming on. Very good question, right? Now, if this reaction is a first one-step reaction, now keep that mind in mind. If this is the one-step reaction, for one-step reactions, right, for one-step reaction. One-step reaction means in single step A and B are reacting at becoming C, right? So one step reaction only, When you balance this equation, we are getting coefficient values. Some whatever value you are getting, right? For example, let's say for A you are getting it as A. For B, B. For one step, single step reactions, only order of the reaction is equal to the coefficient values. Keep that in mind, right? For one step reaction, no single step reactions only. Keep that, otherwise you will think order is always equal to the coefficient value, but only for single step reaction, right? Double step reaction means we don't know. Let's say if this is happening in two steps, maybe A is becoming B, right? And D is reacting with B to become C. So it's a two-step reaction. See, so if this reaction is happening in two steps, then of course we can't use the stoichiometric values as the order, right? The two-step or three-step reactions we can't. So until we know whether the reaction is happening in one step, we can't make an assumption of the orders, right? Is it understood? For two step, or if this reaction is happening in two steps or three steps, we can't assume these stoichiometric values are the order. Order means this one. This is the rate equation, right? This is for the rate equation. Okay. Um, Other thing is, right, in a rate equation, we don't write the intermediates. What are intermediates? Look at this here. So in a rate equation, we don't write the intermediates, right? No intermediates must be written. No intermediates, right? What else? If we are using a catalyst, sometimes you may have a catalyst also. If you have a catalyst, sometimes even the catalyst also included. Sometimes catalyst included, right? Usually, the rate equation is written using the reactant concentrations, right? Written using the reactant concentration. For even for multi-step reactions, right? These are the rules, right? Written. So keep this in mind. Written with reactants only, right? Now, what is the total orders here? A is the order of A reactant. A is the order of A. B is the order of what? B reactant, right? Now remember, order can be any value. Order can be any value, right? Even a zero can be a zero. Even fractions, it can be a fraction. Even it can be a negative values. Usually in our question, we don't give you fractions and negative values. But in case you get a negative quarters, still it is acceptable. Okay. There's no thing like orders should always be positive and whole numbers. So I'm telling you this sometimes. Now in the future you will need these things when you are doing more questions, right? Now, if someone asks you for this reaction, overall load, if someone is asking you about overall load, overall load is equal to what? Addition of A and B. A plus B is the overall load. Simple as that, right? Whatever the values you got there is put here. Overall load is A. Okay? So still we haven't discussed questions, right? Right? So in example, I will give you, let's look at an example question. You are given the stoichiometric equation into gas, H2O gas, right? Balance it, and the rate equation is also given. I will balance it for you. Tell me whether it is a one step reaction or multi step reaction. So, what is the order of H2? Then it is only for what? One step reaction. We don't know whether it is a one step or multi step reaction. If it is a one step reaction, then only you can assume this to be two. Then we can't tell. Right? Here the order is what? Here even when no nothing is written, it is what? It is, yeah, H2 or here two. Yeah, products, right? I my bad. Right. Not can you tell? Is it a first step, single step reaction or multi step reaction? If it is a single step reaction, what should be the, uh, here it must be H2O, right? It's H2. My bad. If it is a single step, so if it is a single step reaction, right? What can you tell about the order of hydrogen gas? Look at here. What is the order? So now here, look at it. Is it two? Do you see two here? Nothing is written, right? If nothing is written, it means one. We don't usually write the one. So it is, even though we are not writing here, it is one. Keep that in mind. Then what do you think? Is it a single step reaction? No. Why? The stoichiometric value is 2. It is here something. So therefore, we can tell it is not a single step reaction. So this is the point most of the time students are getting it wrong. No matter how many times we teach the same concept, again and again they are doing it wrong. Why? In some reactions, stoichiometric values are same as the order, right? So they forget the fact that you cannot decide on the order like that. It is only for single step reaction. If they have mentioned in the question itself, it is a single step reaction, then only you can make an assumption. Otherwise, you can't. Usually, they won't tell you it's a single step or multi step reaction. We have to decide. So it means these reactants are becoming these products with having one or two steps. There are intermediates, and then only it is becoming this. We can make that assumption. It is a multi-step reaction. Is it clear? Okay. I will give another example. I'm giving some points where students are getting this wrong. Let's say uh, A and B is becoming C. And stoichiometric value here is 8. So I'm writing the rate equation as rate equals, what can you tell? I'm asking what is the order of the reaction with respect to B? How do you answer? B is 1. So if it is B, we have it is not written here. Order of reaction. How do you say that? Very good. If it is not written, it means 0. Order of reaction of B is 0. Why? Any number into power of 0 is what? 1. Keep that in mind. So these are the questions they are asking, right? That is why I am at the beginning. I am discussing these things. So you can't tell we haven't discussed. We have discussed. So usually if it is 0, then it is not written. Is it a single step or multi-step reaction? Multi-step, right? The stoichiometric values are 1 and A. Here orders are different. Right? It is happening in multi-step. We don't know how many steps are involved, but definitely not a single step reaction. Right? So it means by deciding on the by looking at the rate equation and the stoichiometric values, we can tell, we can assume whether it is happening in single step or multi-step. Is it clear? Right. Now there's another one important thing. Put the subheading as catalysts and rate equations. These are some things that you guys are getting wrong, right? In a multi-step reaction, if you can remember what you have done in AS, let's say A is becoming B, B is becoming C. This is a slow reaction, this is a fast reaction. Which step is the rate determining step? Slow one or the fast one? Can you remember that? Hmm? Slow one, right? In a multi-step reaction, because I will tell you like this. So now you are going to school. No? For example, let's say now you are coming to coming home by bus. Let's assume. Uh, After school, now school is over. You are running to the bus hold. I don't know whether there are bus holds in where in Middle East, but let's assume, right? That's how things are in Sri Lanka, right? You are running to the bus hold because you want to go home fast. You are going there faster, but the bus is arriving so late and it takes longer time to for the bus to reach home, right? So the time of your arrival to home depends on your journey to school to from the bus to second journey. Slow journey is deciding no matter how fast you are running. Slow journey is what is deciding how fast the whole journey takes, right? Yeah. Still a slow one. Let's say now first one, you are going by bus slowly and they're running. Always the slow one is the rate deterministic. The whole rate of the reaction depends on the slow one. No matter how fast you do, whether it is earlier or later, we are talking about the overall. So overall rate means how fast A is becoming C, right? Whether which step happens faster or slower, it is about how fast A is becoming C. This is the rate. This is the equation, final equation, right? Not this one, right? The how fast C is becoming A depends on the slow one. Right? It could be at the later stage, it could be at the beginning stage. So slow step decides how fast the rate, how far it decides the rate peak. So in the rate equation, all the time, only the slow step reactant is written. Right? Slow step reactant means here K constant, right? So K means rate constant. Keep that in mind. Rate constant. K means rate constant. K means rate constant. Okay. Yeah, we are so in the rate equation you have only the reactance in the uh, slow step into we don't know. Let's say if the stoichiometric value is A, slow step stoichiometric is coming as the order. Slow step stoichiometric value, right? Slow step, not the fast step. Slow step stoichiometric value is equal to the order. Now B is not here. Why? B is at the fast step. Only slow step reactants are written in the rate equation in a multi-step reaction. Right? Write that down. Only slow step reactants are written. And the slow step stoichiometric values are equal to the order. Values are equal to order. That is also important. Right? So stoichiometric value of the slow step is equal to the order. Usually in your syllabus you are getting only two step maximum of three steps. Usually you are getting only two steps reactions, right? In multi steps. Okay. Uh, right. So we are not moving. Only store step reactants are written in the rate equation. Yeah. Okay. I will give you two scenarios. Uh, Rate is equal to K A 2. Find the units of K. Find the unit of K here. See, question here. Find the units of K. Okay. K is equals moles. Mole second. This is the one, right? Now I will give another one. Rate is equal to K B. Find the units of K. Okay. What does it mean? Ah, it is only per second, right? Rate is moles per decimeter. Moles per decimeter. So only you are getting only this one per second this time. So units of K is changing from rate equation to another rate equation. It is not a constant value. K depends, right? Units of K depends. K depends on rate equation, right? And the most important thing is if a homologous catalyst. What is a homologous catalyst? Homologous means what? Both the reactant and the catalyst are in the same phase. Homologous catalyst involved in the slow step, slow step or only step, rate deterministic. If a homologous catalyst involved in the slow step or rate deterministic. So do catalyst. So it depends. That is I'm telling you. Maybe we are using a catalyst to the slow step to make it faster, but still it is not faster than the faster step. We can't tell that, no. We are using a catalyst to make it faster, but still it is not fast enough to beat the faster step, right? Understood? And all if it is only a single step reaction, then anyways there's only one step, no. So only step is the rate determined step in a single step reaction. Right. Homologous catalyst is involved in the slow step. Does the catalyst appear in the stoichiometric equation? Stoichiometric equation. What do you think? Catalyst. No. Do you write the catalyst in the stoichiometric equation? No catalyst in the balanced equation. Balanced equation. But catalyst is not there in the balanced equation, but it appears in the rate equation, right? If a catalyst is involved, so you must wonder in the stoichiometric equation, the catalyst is not there, nothing is there, but suddenly something that is not written in the equation suddenly appear in the rate equation. So they can you can assume it is a homologous catalyst in the rate determining state. But will appear in the rate equation. So the what I am telling you are very important. Just look at it again and again. These things always students are getting it wrong because they forget these things. Right? Always they are making mistakes out of this. Right? There are MCQs, structured essays on these. Okay. Right. Now other thing is we haven't discussed K. Later we will discuss again. K depends only on the temperature. Only on temperature. For the same reaction, you can change K using temperature or with catalyst also you can change, right? Or with a catalyst. The catalyst also you can do it on temperature or catalyst. Same reaction if you are using a catalyst, then the rate is changing, so therefore K is changing, right? With the temperature. Otherwise, you cannot change. Very good. Yes. Then the K must be greater, right? Otherwise, rate is not going up. So very good thinking, right? Those things they are. Huh? Yeah, we are running out of time. So late to next day. Now, actually, we have done most important stuff in terms of rate. There are few things on the mechanisms. Next day, remember me to start with deriving rate equations. Rate equation. Okay, then I'm going to stop it from here. Right? Take care. Bye bye. Okay, you're welcome.